Welcome and thanks for joining us for this episode. We're going to be talking some more today about public and private addressing. And this is something that you might be vaguely familiar with. We're going to bring back some terms that I think maybe you and I have talked about before, whether it's, here in a course or outside in the office. But there's one thing that we need to touch on first, and that is going to be kind of a recurring theme throughout this episode. It's something called RFC 1918. And until we talked about it, I had not heard of it. So let's start there, talk about maybe some of the key elements that we need to know.
Absolutely. I stress, if you're learning networking, to learn some of the standards bodies. One of those bodies is the Internet Engineering Task Force, IaHI. And we have mentioned, kind of like Sophia has talked about, RFCs in general, right? And I've given you some in the past that are really important. This is probably one of the most important ones that you can, if you're just starting out as a network student, to learn. RFC 1918 was published by IaHI, and its purpose was to stall the inevitable depletion of the IPv4 address space. See, IPv4 address space is a 32-bit address space, and if you look at the possibilities, that's 2 to the power of 32, which is around 4.3 billion. All right, we will learn as we go that these addresses were divided up into what was known as classes. 2 of those classes are not used, which means technically we only have 3.7 billion addresses in IPv4 to hand out. You might say, well, that seems like a lot, right? Well, we have 7 billion people on the planet Earth, and I know I could take 10 or 15 of those IP addresses myself because I've got 10 or 15 devices on my network, right? So that isn't going to work. So what RFC 1918 did, IaHI said, hey, you know what? We're going to define the allocation of IP blocks that can only be used in your local area networks. They're private use, all right? Now, I do want you to understand that these IP addresses are not routable across the internet. And there was a purpose for that. They said, hey, rather than you having to come to your local regional internet registrar that's under ICANN and say, hey, I need a block of IP addresses for my internal devices, and they're never going to touch the network or the internet. That'd be wasteful, right? Well, they said, how about we just carve off out of all of these billions of IP addresses certain ranges, and you can use those any way you want. You don't have to go to ARIN. That's our American registry or American registrar. It's ARIN's the registry for North America. Thank you. I can see Sophia helping me out. It's been a while since I've looked at it. All right. And I can use these no matter, any way I want. Here's the other good thing. Let's say Sophia, she's got her network, right? Well, she can use the exact same IP addresses that I'm using right down to the last bit. Why? Don't IP addresses have to be unique? Well, yeah, they do. If they're routable across the internet, they definitely have to be unique, but they have to be unique within your local LAN if they're private addresses. Those addresses do not travel from my network to Sophia's network, and that's one thing that we have to understand. So it did help, but you can only use them in your local area networks. They're not routable across the internet.
The thing you were talking about, ARIN, is it the American Registry for Internet Numbers? Does that sound right?
That's it. They are the North American. So here in the United States and Central America, Mexico and stuff, that's where we would go if we need to get public IP addresses, right? Okay. Now, this is going to be more of a focus on the private IP addresses, because anything else that isn't public or a private IP address is a public IP address.
Okay.
All right. So I'm going to show you some ranges, those blocks that are carved out, right? And I want you to know that anything outside of that block is a public IP address. All right. And now that means if I was to get one of those, I'd have to go to somebody like ARIN. Typically, you'd go to an internet service provider, and they've got IP addresses to lease you that have come from a larger ISP all the way back up the hierarchy of the internet. All right. And that IP address is routable across the internet. It's called a public IP address.
Okay.
I want you to be aware of that. But what we're going to focus in here more so than anything is RFC 1918 and the definition and implementation of private IP addresses that are non-routable across the internet.
Okay, that's good to know. So it's a better question to ask, there's going to be more public IP addresses than private, generally speaking.
Yes.
Anything that's not private is public by default. Okay.
Yeah.
So you mentioned earlier, you said something about different classes. So I think you said Class A. as far as real world networking, where does RFC 1918 and classes like that, where do those factor in? How do they work?
Okay, so in the private IP address blocks, you'll see that there is something, well, really in IP addressing, those 4.3 billion that we talked about, we'll have an episode that really dives into the classes, but it's a classful system. In the days when it was a classful system, it was divided up into classes in which you needed a certain amount of networks and maybe a large amount of nodes, or maybe a medium range of networks and a medium amount of nodes. Or then finally they had one that's like, hey, I don't need more than 300 nodes on my network, right? So you have private IP address blocks that, depending on how you use them, could scale up fairly large, all right? And what I mean by that is you have some in the A range, and I'm going to show you what I mean here in a second, that a single network in the A range private IP address could give you 16,777,214 nodes on a single network. You could have 16 million devices, almost 17, on a single network. That's a large network, all right? Those A addresses that are in the public range, they go to companies back in the 90s and even earlier, like Apple. Apple's got a block. There was a car, I think GM had a big block, millions of addresses, because back in the day, they thought they were going to have an IP address in every one of their cars. That didn't work out, but they still have the block. All right. The mid-range would give you about 65,534 devices on a network. All right. And then the final range, and we're going to show that. I don't expect you to just know this from memory. I'm going to show you what I'm talking about. The final range only gives you about 354 nodes on a network. So where do we see these? Well, if you're using A and B, these larger type networks, again, 16 million or 65,000, still a lot of computers on a single network, then you're probably going to be some kind of corporate network or even a data center, right? When they can now make a collection of data centers and put an abstract layer over it where it looks like a massive data center, right? Well, if you have those large amount of devices, then chances are you're probably going to use a class A or at least a class B. You need more than 300, right? So it is important to understand that you have a different amount of devices that you can put on these, and that's really going to define which range is suitable to you. Now, one of the things I will say, doesn't matter which one you use. Sophia can use 10 dot. I'll show you what I mean here in a second. I could use 10 dot on my networks. Well, why don't they conflict? Because they're not routable. I've got to keep saying that because it tricked me up. I'm like, why can I use all these? But wait, you're using these over here too. Why? They're not routable. They're private. All right. So you have, keep in mind, corporate networks, data centers, A and B. You have the home networks, probably going to use one of the C private IP address ranges.
Okay. Well, that makes sense. And it's kind of nice to hear how this is used in real world networking, because especially for if you're trying to learn or if you're studying for a well-lit room situation, then it's good to be able to connect it back to, oh, this is why I need this information.
Absolutely.
This is why it's important. I know going through school, that was a big thing for me. So one thing that I mentioned earlier is that there was this term that you and I have talked about before that's going to kind of come back into play, something called NAT, Network Address Translation, I believe. So how do RFC 1918 addresses interact with NAT?
Okay, so part of RFC, the RFC 1918 was is NAT. NAT is built into that specification, and what it does is it provides us with a way, I'm going to confuse you now, to make private IP addresses kind of routable. Let me show you what I mean. All right, so I've got a basic network here. Don't worry about what the first octets are. We're just going to call them private IP addresses, right? For now, I'll define this in a second, right? So what ends up happening is this device will send information, it'll send a piece of data right to the router. And the router, we want to send information past our local router, right? Well, remember, for it to be routable, it has to be a public IP address. So this private IP address that's on the LAN is not going to work. So let's look at a little packet manipulation. The router here also has a public interface, and that public interface has been given a public IP by the ISP that this company has, basically leased it from, all right? So we have a private IP address on the interface that's connected to the local area network. We have a public IP address that's connected to the WAN link or the ISP's provider, and when this computer on the internal network with a private IP address sends information to the router has a table in it. and it looks and it says, oh, you know what? I see that source IP address. Notice it's private IP address. So what I'm going to do is I'm going to go ahead and remove that source IP address. Remember, it's coming from inside of our network with a private IP address. And what I'm going to do is I'm just going to go ahead and I'm going to remove that address right now. And what I'll do is I'm going to change and put the public IP address of the router interface. And we're going to send it on its way. So now we have a routable data packet with a source IP address of a public source IP address. Now, from the rest of the world standpoint, all they see is the router. They don't know behind that router is actually a computer that had a private IP address that sent that communication in the router, and it did all of that packet manipulation. But that is what network address translation, in a nutshell, does. When that information comes back in into the network, comes into the router checks its table and says, oh, I see that was the private IP address. Let me go ahead and I'm going to replace this just like we had before, and I'm going to deliver it to the local network. That's network address translations, translating private IP addresses to public IP addresses. So those private IP addresses that typically aren't routed, they still can't be routed, but we can still have routable communications with NAT.
Oh, that's kind of like a loophole.
It is. That's a great, it's the parenthesis clause. It's the if in the contract.
Yeah. Oh, interesting. Circumventing some things. Okay. Well, not really, because it's not like it's below board. Like it's not like, oh, this is a bad thing for you to do.
No, it's actually a good thing. And you know, I'm glad you kind of, you jogged my memory on something, right? Here's the one good thing. I didn't tell you how it applies to the depletion of the internet's IP addresses. How does it actually work? Well, here's the thing. Every single one of these devices has their own private IP address, but network address translation will let them translate all of those internal private IP addresses using just a single public IP address. So I now have 1,000 devices and servers behind my network that before RFC 1918, if I wanted them to connect to the internet, I'd have to have 1,000 public IP addresses. Well, get your bank books out. That's expensive. But now with network address translation, we can sit them behind the router. We can give them all private IP addresses, implement network address translation on the router, and we use a single public IP address to translate all those internal private IP addresses. That's where another one of the benefits go. And I'm glad you kind of jogged my memory on that one. Got to mention that, or we don't know how it applies to that depletion I was talking about.
You did also briefly earlier kind of touched on, you said something about, oh, if you use something in the 10 dot range. So are there different like private address ranges? Absolutely.
And you know what I've done in the past, Sophia, is I've just put a list up here and said, hey, here's the list, memorize it. I'm still going to put that list up here, but what I'd like to do is show you, I've got 3 different network examples using all 3 of the different private ranges. And I think it might be a little bit better to help solidify it in your memory. So let's go ahead and take your Dramamine. We're going to do a little manipulation here because there's a lot of stuff here. So what I'm going to do is I'm just going to show you a basic network. All right. And I want you to see that this network is using 10 dots, right? For all of our computers here, right? We're doing 10 dots, excuse me. And I just put the last octet in every one of the computers here to represent that last octet right there. But that is a Class A private IP address range. How do we know? Well, let's go ahead and I can tell you that I can see here's our network ID, broadcast address, default subnet mask, usable range, and the private IP address range. Here's what I want you to pay attention to. Notice that last portion of this table. That's your homework. Your homework is that the private IP address range for 10 dot is 10.0.0.0 to 10.255.255.255. Wait for it. One more. .255. All right. That is the A range, right? Now, for those of you, some of you might have been a little bit farther in your journey. Maybe you've watched some of the other episodes that we have here at ACI Learning. You could take a pause and you could see what the network ID is, the broadcast address for this network. The default subnet mask is another thing that we have to talk about. In the A range, the default subnet mask is 255.0.0.0, or if you're saying CIDR notation, it's /8, 8 bits in the mask. All right, I want you to know that. That is the Class A range, and this is an example of a network that uses that Class A range. All right. Now, let's go ahead. Let's go walkabout. All right. Try to do it slow. Don't want to make anybody seasick. And now I have one that if you were to pause the video and look at it, you would see that I now have one set up as a Class B private network. Notice the IP addresses, 1.16.16, see it's just .0, .1, .2, .3, .4, and then I've got my default gateway, which is the router connected to this network on the upper end of that range, okay? So what is let me change this on the fly. Apparently I did not change that. This is supposed to be Class B, and this is how this network is set up, and it's going to be important for you to know some of the information on this one as well. All right, so homework. This is what you need to make flashcards out of. Your Class B range is 172.16.0.0 to 172.31.255.255. It's probably one of the weirder ones that maybe, because we go these nice even 255s, and this one is not 255.255.0.0. It's actually 255.240. All right. As we talk about subnet masks and stuff like that, we'll talk about why that is a valid subnet mask. But that's why you get these weird, not so evenly divided numbers here. It is right. It's 172.16.0.0 to 172.31.255.255. Now, I did mention something kind of in passing, Sophia. And let me help me out, and hopefully this will make sense to you as well. Ladies and gentlemen out there, all of you, I want you to know that, remember what I said, anything on the outside of these is public. So if I have a 172.15 address, .0.0, well, it's not an address, that's a network, that is public. If I have a 172.32.0.1, that is a public address. It's on the outside of that range. More homework, okay? If it's on the outside of that range, it isn't private, it's public. And it's an easy way for those of you that are, would you say, Sophia, maybe answering questions in a well-lit room? Yeah. So I will tell you some of the things that I'm telling you, everybody out there. If you're on a help desk, you can Google this stuff. But exams don't let you do that. So hint, hint. All right, last one. We're going to do an example of a Class C. Notice the IP address ranges. I got .1, .2, .3, .4, and I put my default gateway on the other end of the IP address range. That's just something I do. You don't have to do that. All right, notice that we've got all of our computers have our same .1, .2, .3, .4. Now, the reason I'm using the same host portion is because I want you to know, I want you to see the subtle differences in the private IP addresses so that you can identify them on an exam. That's going to be important, right? So I try to keep the host numbers just even because I don't really care about them at this point. What's most important, like I said, everybody, is this right here, right? I've given you, those of you that are a little bit farther in your journey will understand what these make. The network ID for a Class C address is going to be 192.168.0.0. The broadcast address on the other end of that spectrum, remember, is going to be .255 in the last octet. The default subnet mask, 255.255.255.0. That is 24 bits in the subnet mask if you're doing CIDR notation. All right. Now, what is the range? 192.168.0.0 all the way to 192.168.255.255. If I have a 192.167 or I have a 192.169, those are public addresses. They do not fall in the private range. And that's very, very important. And that's why I wanted you all to be aware of this, right? I used to just put a whole bunch of, slides up and it'd just be all kinds of flashcard material. It still is flashcard material, but hopefully you can see that when these are implemented like that, I can implement any one of these ranges. It really just depends on what scalability do I need in my network.
I'm glad you reminded me that if it's outside of that range, it's public, because my first instinct, if I was going to take some kind of an exam in theory on this, would be to say, oh, well, the Class A range starts with 10 and Class B starts with 172. So I just got to look at that. And if I can remember those three numbers, I'm golden. And that's not necessarily true, because if there is a question that's a little tricky, oh, well, it starts with 172, but it's 172.17 or not 15, and that's outside the range. So glad you clarified that.
Yeah, a bit matters.
Yeah, a bit matters a lot. So.
Great, I like it.
So don't forget that. So one other thing I wanted to touch on before we wrap up, you had mentioned earlier that because these are private addresses, it prevents external traffic from reaching them. So these are maybe more secure to use?
there's I think it's obscurity. It's security through obscurity. Obfuscation, I think, is
Okay.
it's security through obfuscation because the data's in that packet. Like when we talk about the OSI model, they could find the internal address, but not easily,
Mm.
right? So it can assist security, but we know that security through obscurity isn't really secure. There's ways that they could find the information, but as at a casual glance, the blinds are closed and you can't see what's on the internal network. So from that standpoint, I would say, but I don't want to give somebody a false sense of security, thinking that somebody that knows their network protocols and stuff, somebody's doing penetration testing or doing, maybe the other way around, maybe you're doing auditing, that they couldn't find this information. Because again, remember the OSI model wraps those layers. That information's in there somewhere, but what you do when you overlay NAT on it, what you're doing is you're only manipulating the source and destination IP addresses. So it obscures the internal private IP address, and that at basic glance you can't see the internal what the internal private IP address numbers are.
Okay, so maybe it kind of reduces the risk.
I used to say security, but then if you talk to somebody like Anthony, who's a CCIE, he'll tell you that, and I'm not putting words in his mouth, so I apologize, but it's not really security, right? It's not like saying, hey, we have a firewall, you can't see anything, right? We're just obscuring the fact that it's there, right? But if somebody has the capabilities, they can see the data, they could deduce what's going on in the internal network.
If somebody really wanted to get to it, they could.
Absolutely. So you can add a layer of obscurity to your defense mechanisms, but you're going to use your firewalls, IDSs, and all that.
Of course, you never want this to be your only defense.
Absolutely.
Because it's not a defense.
You got it. Layered defense system. Couldn't have said it better myself.
It always comes back to that, doesn't it? Well, as far as, like I said, RFC 1918 was new to me at the start of this. So now that we've kind of gone through it, I'm glad we have an understanding of this. And it's stuff that I see those IP addresses in our work here all the time. I see you and Dan refer to, this IP address, 192 dot such and such. So it's good to kind of have some context with that now. And we also talked about, like you said, how it can add a layer, but it's not the only security that you want to rely on. I think that's pretty much going to do it for this episode. So thank you for walking us through that, Wes, and thank you for joining us. And we'll see you next time.